Last video we looked at what the normal distribution curve was. We're now going to start putting that normal distribution curve into practice so that way you can see how the different parts of this normal distribution curve can use to help us work out different possible results. So what we're looking at today is we're looking at a normal distribution curve where the mean and deviation, the two different examples, are going to be different. However, all the information within it doesn't change. The percentages don't change. How many places we move to the left and right don't change. It's what changes in terms of the mean and deviation. So if we look at this question we've got up here, it says the distribution of blood pressure readings for executives is normally distributed with a mean blood pressure of 134. So we've got a mean of 134 and a standard deviation of 20. On the diagram below, we want to clearly write on the axis the numerical values of mean plus and minus deviation, mean plus minus 2 deviations, and mean plus and minus 3 deviations. And then we want to write the percentages. Well, we've got the percentages on here already. Okay, we know we've got 34, 13, 2.15, 0.15 there. So what we're going to look at here is now we're going to put our information down. We know that the mean is 134. So 134 plus 20 is 154. 154 plus 20 is 174, and 174 plus 20 is 194. 134 minus 20 is 114. 114 take away 20 is 94, and then 74. So what we've got here now is the lowest possible blood pressure for the executives is 74 up to the highest possible of 94. And this just represents, remember, that's one deviation away, 2 deviations, 3 deviations. So 3 parts away from the mean, 3 parts away from the mean. So let's look at this here. It says, from this information it became concluded that about 68% of the executives have blood pressures between. Remember, 68% was one deviation away from the mean on either side. So this will be the left-hand side, so 114. This will be the right-hand side, 154. About 95% of the executives have blood pressures between. Now the 95 was 2 deviations away from the mean on either side. So the lowest part would be 94, and the highest part would be 174. And then the last one, about 99.7% of the executives have blood pressures between, well, that's 3 deviations away. So 74 to 194. So you can see by using those small 68, 95, 99.7, we're able to show what range within this normal distribution curve the information we're looking for shows. We now look at this next question. It says about 16% of the executive blood pressures are above. So if we're looking for above, we're looking for something on the right-hand side. And this is where those percentages come into place. We know that if we add all these up, we're going to get about 50%. But we only want 16% of that data. So we know we've got 0.15 plus 2.15 gives you about 2.3, plus approximately 13.5, which gives you that 16%. So all this part here is the 16% of people that have blood pressure above 154. So because it's above it, we're looking at that right-hand side. So if we did it on this side here, that wouldn't represent 16%. This actually is a 50 plus 34, so that would be 84% of data is above it. But we're looking for 16, so about 16% of the executives have blood pressure above 154. Okay. About 0.5% of the executives have blood pressure below. So now we're looking at the below, we look at the left-hand side. So if we're looking at 0.15, it's going to be below 74. Now if you think about this very carefully, a lot of the statistic questions are going to be based off real life things. If you're an executive, you're going to be in a very stressful, high impact job. So you're going to expect to have some high blood pressure. So most of them would have above 16%, would have 54, and the lowest you possibly was 74. Now the last part here is about 50% of the executives have blood pressure above. Well, 50% is your middle part. So what we've looked in this example here is we've looked at our distribution. The percentages haven't changed, but the deviation and mean have changed. And that changes our variables in this case here. Let's have a look at the second example. Bring this up. All right. So the second example is a little bit different. It's different in the fact that we have a different mean and different deviation now being used, and we've got different ways of answering the question. So it says here, pet food is sold at 450 grams, which is packed by a machine. It is known that the weights are normally distributed with a mean of 456. So a mean of 456 and a standard deviation of 5. Below on here, let's write out the variables for mean and plus minus deviation. So we know it's 456, okay? We know if we look at these points here, we can say we've got our 34, we've got our 13, a 2.5, and a 0.15. So 456, if we add 5 to that, we get 461, 466, 471. We take 5, we get 451, 446, and 441. So they're our new mean and deviations. The percentages haven't changed, it's still exactly the same as before. When it comes to normal distributions, we usually denote this by using a simple method. We will say x is approximately n for normal distributions, mean, and standard deviation. So this here is a way that you would write your distribution. So in this case here, we'd have x is normally distributed to a mean of 456 and a deviation of 5. The approximate range of the weights of the boxes is between, well, 441 is your highest, and 441 was your lowest, sorry, and 471 is your highest. 68% of the weights are between, well, they're between one deviation above and below it. So 451 and 461. Approximately 16% of the weights are greater than what? Again, we're looking at the 16%. So that's looking on this side here again. So 16% is going to be greater than 461. And if we shade that area in, that's that area that represents that 16% of people cans are greater than 461. It then says approximately what percentage of pellets have weights greater than 466. Well, this was 34. This here was 13.59. This is 2.15 and this is 0.15. So what we're doing here is we're just adding these two together. So the 2.15 plus the 0.15 gives you approximately 2.30 or 2.28 if you want to be a bit more exact. Then the last example here is then, well, using this, how many cans will be weighing more than 466? So in this case, you just do 0.023 times 5,000. And if I get my calculator out, let's do that here. That gives you approximately 117 cans. So what we've looked at in this example here, the second example, is how we use the normal distribution. And what I want you to notice is that the only things that are changing in the normal distribution curve are the variables down the bottom that represent a mean and a deviation. Your percentages, your your deviations don't change. They will add up to the variables that we're looking for in this case here. So for instance, if I wanted to work out what percentage of cans are greater than 451. So we're looking for percentages greater than 451. Well, here's 451. We know from here to here is 50. If I add another 34 on, then 84% of the cans are going to be greater than 451. Okay? If I did it the other way around and said, well, how many of the cans are going to be less than 451? Well, less than is all the data on this side here. And I know that if I add these three up, that gives me approximately 16%. So 16% is less than 451. Our next lesson, we're going to be looking at graphics calculator steps with this, because we are going to get examples where we're going to try and find out what percentage sits between these things here. And we don't want to make a guess, we want to get some exact calculations. And unless you, if you don't have a calculator, you're going to have to use a very specific formula. Lucky for us, we have calculators. I'll see you then.